got a quadrupole mass spectrometer sitting inside it to analyse the oxygen level that's sitting in there. And then that feeds back to this primitive bit at the just top of your spinal column, at the base of your brain, which then tells you how to breathe. Well, that's easy. So now we've got an oxygen sensor sitting inside here, which is doing a phenomenal job, and it's measuring down in parts per million. There's more. Carbon dioxide, peripheral chemoreceptors also monitor the carbon dioxide concentration in the blood. In addition, a central chemoreceptor in the medulla monitors the carbon dioxide concentration in your cerebral fluid. So sitting in your base of your spine is this little thing down here, the medulla, and this, all the blue stuff, is the goop around your brain. So that when you do that, if you feel a sloshing sound, it's because of that. It protection stuff. Some of you, when you go sideways, you hear brrr, that's your brain rolling sideways. Okay? Now, this thing monitors the amount of carbon dioxide in this because the brainal fluid is very absorbent of carbon dioxide. If you get carbon dioxide in there, your brain stops. I've met a few people like that. Okay, so this cerebrospinal fluid that surrounds the brain and spinal cord, carbon dioxide diffuses easily into it from the blood. If the carbon dioxide concentration gets too high, then both types of chemoreceptors signal the respiratory sensors to increase the rate and depth of breathing. So you've not only got something sensing the amount of oxygen in your bloodstream, you've got something sensing the amount of carbon dioxide in your bloodstream and the amount of carbon dioxide in your spinal fluid. Now, how does it get round? You haven't got something that's pumping your spinal fluid around because it goes right down your backbone. But somehow it does it. So we've now got, sitting in the aorta up here, which we thought was a simple pipe, is it measures the oxygen, which goes back to the medulla. It measures the carbon dioxide. Within the medulla, it also measures the carbon dioxide sitting inside your brain fluid. And then it feeds all that back to how you're breathing. So this is simple. Well, there's more. Sorry about this. There's hydrogen ions. There's a thing called pH, which is how acidic or how basic a thing is. The peripherals and central chemoreceptors are also sensitive to the pH of the blood and sitting inside your spinal column. Now, if it's like vinegar, it's too acidic, and if it's too basic like soap, then you die. And it has to be kept very, very accurately. Now we know how to do that. You've got a thing called a swimming pool tester, and you pour water in there and you look at the colours and all this sort of stuff. This happens automatically inside your body though. So it's not only measuring carbon dioxide and everything, it's also measuring the pH, how acidic or how basic your blood and your spinal fluid is. So now we have it. We've got sitting there in the aorta, it measures the oxygen, it measures the carbon dioxide, and it measures how acidic it is. We're now up to 3 pieces of equipment which if you had it, you wouldn't be able to carry them all. Then it also analyses the carbon dioxide and the pH that's in there, which then leads back to your breathing. Isn't it amazing? All this happened by sheer chance. It's good. And finally, chemical irritants. Nerve cells in the airways sense the presence of unwanted substances in the airways, such as pollen, dust, noxious fumes, water or cigarette smoke. The cells then signal the respiratory sensors to contract the respiratory muscles, causing you to sneeze or cough. You ever been walking past and someone's blown cigarette smoke into your mouth and you go, that's because of these. And signals from the higher brain sensors, nerve cells in the hypothalamus and the cortex, also influence the activity of the respiratory centre. During pain or strong emotions, the hypothalamus will tell the respiratory centre to speed up. When you're sitting there under a lot of stress, you go, So, it's really simple. So now we've got, sitting inside this little simple tube is an oxygen, carbon dioxide and pH tester which talks to the medulla, which is a very primitive area and can't do much at all. And it also measures the carbon dioxide and the pHs in the brain fluid. It feeds that all back, plus there's stress, plus there's the chemical irritants in your nose, all feeding back to this little thing which are then telling you to breathe. What a design. What a design. So the air finally gets to the lungs. Okay, now it starts to get simple. There are some 300 million alveoli in 2 adult lungs. These provide a surface area of some 160 square metres, almost equal to the singles area of a tennis court and 80 times the area of our skin. So you're sitting within your lungs, you've got this huge amount of area. What's even more amazing, for every little bit of your lungs, there is blood supply going through to it. If you had only blood supply to a small part of it, the rest of your lungs wouldn't work. These little pipes have got to go through every slight little bit. So when your heart goes kapoomph and pumps, it's pumping blood through a tennis court of skin. And then it pumps it all back again, back up to the lungs when it's oxygenated, and that pumps the rest of the body. 160 square metres of the stuff. Air comes in, oxygen passes through the lung wall into the blood, carbon dioxide comes from the blood through the lung wall into the expelled air. Easy. You breathe in, oxygen comes through, you breathe out, carbon dioxide goes out. Not quite. Here you've got air up here, you've got a thin lining, and then you've got the blood supply going through, and it's giving up carbon dioxide and taking up oxygen. This barrier between the air and the blood has an average thickness of 1 micron. This little layer that protects your air, the air and the blood, separates them, is 1/1000th of a millimetre thick. 1/1000th of a millimetre thick. Oxygen passes quickly through this air barrier into the blood and the capillaries. Similarly, carbon dioxide passes from the blood into the alveoli and then is then exhaled. 1/1000th of a millimetre. If you take a hair, if you're like me, your hair is in fact quite thin at odd places, and if you are Asian, you've got a fairly thick hair, so 150 micron. So if you took one of your hairs out of your head, I won't because they're precious for me. If you take a hair of your head and the average person divided by roughly 1/100th of a hair width, that's what this little layer between the blood and the air is. Some interesting things. If you cut yourself, the blood clots rapidly, doesn't it? Yes? Yes. Good. 3 people are awake, the rest of you are asleep. There's only 1/1000th of a millimetre layer between the blood and the air in your lungs. If this wasn't just right, then you would either die from lack of oxygen or your blood would clot, scab in your lungs. If instead of 1/1000th of a millimetre it was 3/1000th of a millimetre, you'd die. You can't get the oxygen through. If instead of 1/1000th of a millimetre it was half that, the oxygen would get through, your blood would say, oops, I'm cut, and you'd get a clot in your lungs. It is exactly the right thickness. And if you want to talk about diffusion models of how the oxygen goes through, they've done all this lot, and it turns out it is exactly the right size. Exactly. If we were designing it, you'd spend a few hundred years, and you'd design it, it would be exactly 1/1000th of a millimetre thick. So when you cut yourself, it clots. When you breathe in, it doesn't. And then you have the gas transfer. You've got oxygen here in the lungs. Hang on, we've lost it. Oh, there it is. You've got the oxygen and the carbon dioxide over here. It goes through this little 1/1000th of a millimetre into the bloodstream, and then it transfers off into the hemoglobin and the red blood cells, and then that goes through and works all sorts of stuff. And it's a really simple equation of how it all works. Oxygen goes into here and it does that, and this moves across there, and the carbon dioxide comes out through here through a carbonic acid and a carbonate, and out through here and all sorts of stuff. If any one of those were there, you'd die. How does it work? Very complex. Also, the red blood cell has got a maximum surface area for the shape, and so it enables it to work. All this sort of stuff. So the oxygen goes through into the plasma, and from the plasma into the red blood cell. Must occur in thousandths of a second. When the red blood cell is going past the capillaries in the lungs, you've got to have carbon dioxide comes out and oxygen goes in thousandths of a second. It's the fastest rusting process that we know. If it didn't, again, you would die. So this is an amazing design. And all this happened by chance. Dust removal, humidifying the air, medulla feedback correction, aorta sensing the oxygen accurately, diaphragm in the right place. You ever thought if you were evolved with your diaphragm on your